Project 130, Morse code, is going to tell you about a very interesting piece of technology that we might now take for granted or no longer use. Before the invention of the telephone, Morse code was used to communicate with people from long distances away. It is called Morse code because it was invented by Samuel Morse in the 19th century. And Morse code consists of a series of dots and dashes, which are used to represent letters, numbers, and punctuation marks. The telegraph has only two states, either on or off, which means respectively transmitting or not transmitting. This circuit is going to resemble a telegraph, and I can explain to you how it works. Its operation is pretty similar to previous projects, but now I will explain to you about its operations. Here's just some more information about it. I'm not going to explain it all, and I'm certainly not going to demonstrate all these letters and numbers, but I will explain to you how they work. For instance, if you want to do the letter A, you would do a dot and then a dash. A dot would be like a short transmission, a short burst. That would be a dot, and then a dash would be like that. Now, I am going to spell my first name, and I'm going to ask you to guess what it is. You ready? Now, if you guessed properly, my name is Andrew. It's possible that the slide switch did not make contact all the way with the last dash for the letter W, but I was indeed spelling my name. Now, if you had a much longer fiber optic cable and another circuit like this, you could communicate with friends even if they were a very long distance away. I'm not going to do this, but if you want, you can switch the locations of the red and white LEDs. Now note that the white LED requires more voltage to operate. If it's not operating properly, even though it is in this circuit, you may want to use the color LED. But thank you very much for watching this demonstration on Morse code. Project 131 is fiber shutoff. We're using the same circuit, but we switch the locations of the phototransistor and R5 resistor. The positive end of the phototransistor will remain away from me. And you'll see that the white LED is on, even though the press switch is not being pushed. But when I push it, the red LED comes on, but the white LED turns off. When I release it, the white LED comes back on. That's because the phototransistor will only operate the white LED will only operate when there's no light on the phototransistor. When there's light, it will turn off. So you could still pretend to send messages, but except now when the LED is off, that means that a message is being sent. Like this would be I did explain to you about dots and dashes in the previous project, obviously, but if we were using this circuit, this would be a dot, and then this would be a dash. But it will probably be a lot more confusing to your friends unless you explain to them clearly how it will work if you were going to use the reverse principle for sending messages to them. Project 132 is blow-on fiber. This project uses two separate circuits, and the larger one on the left contains the color LED and microphone, and the fiber optic cable is connected to the color LED using the white holder. On the right is the red LED, slide switch, and phototransistor, in which the other end of the fiber optic cable is attached to with the black holder. I'm going to blow into the microphone and watch what happens to the red LED. When I blow into it, the red LED lights up because it is enabling the color LED to become brighter and therefore be able to transmit to the phototransistor and light up the red LED. In the current state it's at, it's off right now, but it should come back on, but at a dim level. It cannot activate the red LED. There's not enough light on the phototransistor. But once I blow on the microphone, it becomes brighter, and there's now enough power to activate the LED. Project 133 is fiber music. We are going to use a music device hooked up to this project, and we'll turn on the slide switch. We're also using the fiber optic cable, which is connecting the color organ and phototransistor. And when I hit the play button on my music device, a song will play, and the color LED, color organ LED, will flash and change colors according to the beat of the music. Also, the red LED will be on, and it will be blinking according to how the color organ LED is changing colors and flashing. That's because the light from the color organ LED is traveling through the fiber optic cable to the phototransistor, which will then power the red LED. If I pause the music, the color organ LED will remain at one particular color, but because it's still lit, the red LED will remain on as well. If I was to disconnect the fiber optic cable, the red LED will turn off because light cannot get to the phototransistor now. Once I plug the cable back in, the red LED is back on. Project 134 is fiber color organ. We are going to use this circuit, which includes the microphone, color organ, phototransistor, red LED, and fiber optic cable, and it is connected between the color organ and the phototransistor, and we are going to turn on the slide switch. Nothing happens, although when I'm talking, the microphone picks up my voice and the color organ changes colors. Also, look at the red LED as I continue to talk. I could also blow into the microphone, but as long as the color LED is on, the red LED will be on as well. But my voice is once again changing the colors on the color organ. You do not have to do this, and this is optional, but you can plug in a music device and it will control the LED on the color organ. You won't hear any sound because there's no speaker, but now it's controlling the flashing of the color organ. But still, when I pause, now, once I pause the music, you can see that the color organ LED is now off, and so is the red LED. Now, if I blow into the microphone, it's not as sensitive when my music device is plugged in. The color organ LED will change colors. Disconnect the music device, and now the microphone is more sensitive. Project 135 is bright fiber color organ. We are going to use this circuit, and I'm going to turn on the slide switch, and as I talk into the microphone, you can see that instead of the red LED coming on, it's the white LED. We're using the white LED, and it's very bright. It's much brighter than the red LED. And in this circuit, the microphone is very sensitive, and it changes the color organ as I talk, even from this distance. And my mouth, I would say, is at least 1.5 feet from the microphone. And so it changes colors quite easily. Whenever the color organ LED is off, so is the white LED. 136 is motor power. We are going to use this circuit, and we are going to look at the brightness of the red LED as well as sound that comes from the speaker when the motor is spinning. We can use this circuit, try this circuit in 3 ways. 1, when the fan motor is spinning without the fan. 2, when it's spinning with the fan attached. And 3, when the motor is on while I am holding it with my fingers. Now, it's recommended you be careful when performing that phase of the project, but I'm going to start with the first phase. You probably hear noise from the speaker as the motor spins and the red LED comes on. And you can see that it's pretty bright. Now I will put the fan on the motor. Make sure it's mounted on securely. And you hear sound from the speaker and the red LED comes on, but it may not be as bright. I could be wrong, but it may be slightly dimmer when the fan is on the motor. Now I'm going to hold the motor with my fingers and hold down the press switch. Once again, you should be extremely careful when doing this yourself. You may hear clicking noises from the speaker as the press switch is making contact with the circuit, but the red LED does not come on, even though it blinks when you push and release the switch. When you let go of the motor and hold down the switch, the red LED comes on. The reason why the LED does not come on when you're holding the motor is because the motor requires a lot of electricity to begin spinning, but the faster it's rotating, the less power it needs. When you're holding the motor, it is sucking up all the electricity, leaving none for the red LED, and that's why it will not come on. But when the motor is spinning without the fan, the LED has the most electricity than if it is spinning with the fan. Project 137 is more motor power. We will repeat Project 136, but we will use the white LED and then the color LED. So I'm going to quickly go through the phases. Phase 1, white LED is fairly bright. Now with the fan, the white LED doesn't really come on. It flickers when the press switch makes contact, but that's all. And it will definitely not come on when I am holding the motor and the press switch at the same time. Once I release the motor, the white LED comes on as it spins. Now we will use the color LED. And it comes on even though it doesn't really change colors. It's very, very dim, and it's mostly red when it's just only red when the fan is on the motor. And now we will hold the motor and the press switch at the same time. Nothing happens. Like what I explained in the previous project, the motor uses all the electricity when I am holding it, and that's why the LED will not come on. But when I release it, the electricity can flow through the rest of the circuit. Project 138 is Reflection Detector. This project is interesting in that it will literally detect the reflection of light. This circuit uses the white LED, phototransistor, and the color LED, and note how we place the attachment holder over the phototransistor. And that's for a good reason, and you'll see why. We are supposed to move the lever on the adjustable resistor all the way to the NPN transistor, and then we will need a mirror for this. We could either use a handheld mirror or a wall mirror. I'm going to use a handheld one, but this isn't just any regular mirror. This is the light tunnel from another Snap circuit kit. And a bonus for this project is that, can you guess what kit the light tunnel comes from? I'll just leave it up to you to decide. I'm not going to tell you, but it is a mirror too, and we can hold it over the white LED. And watch what happens to the color LED. The color LED comes on even though there's no direct light being shined onto the phototransistor. Why is that? That's because the mirror is reflecting the light from the white LED back onto the phototransistor, and that is triggering the color LED, meaning that a reflection has been spotted. The mounting base on the phototransistor just keeps other light from it. And they say that if your room is very dark, you might have better results if you put the mounting base over the white LED instead of the phototransistor. But because there's still some light here, it will not work. Do it again. When I take away the mirror, the color LED turns off because the light is no longer being reflected into the phototransistor. Project 139, cup and string communication, is only going to be a description and not a demonstration. You will need certain parts for this project, and you don't actually need a circuit for it. You will need 2 cups, 2 paper or plastic cups, a string, a pencil. Light, radio signals, and sound all travel through air like waves travel through water. And to understand this principle better, you can make a telephone from a cup and string. This trick requires some household materials. They're not included. And the best string to use, by the way, is non-stretchable thread or kite string. Make sure you have a sharp pencil as well, and adult supervision is recommended for this. Take the cups in, punch a tiny hole in the center of the bottom of each one with a sharp pencil or something similar. Be very careful, though, not to hurt yourself or others. Take a piece of string that's between 25 and 100 feet and thread each end through each hole. Either knot or tape the string so it cannot go back through the hole when the string is stretched. And then with 2 people, have one person hold one of the cups and spread the cups apart until the string is completely tight. Once the string is in a straight line, if one of you talks into one of the cups, the other person might hear what they are saying. And then that person can talk back to them, talk back to the first person, and they should hear it as well. How does this work? When you speak into the cup bottom vibrates back and forth from your sound waves. The vibrations will travel through the string by pulling the string back and forth, and then make the bottom of the second cup vibrate just like the first cup did, producing sound waves that the listener will hear. If the string is light, the received sound waves will be just like the one sent, and the listener hears what the talker said. Telephones work the same way, except the electric current replaces the string. And in radio, changing current from a microphone is used to encode electromagnetic waves sent through the air, then decoded in a listening receiver. So that's how radio works, basically. And here's some diagrams that show two users pulling the cup so that the string is taut. And then here's a graphic showing a pencil being used to make a hole in the bottom of a cup, and another that shows a knot being tied in the string in the cup. And so with that said, thank you very much for watching this description.